I welcome you all in this course on steam and gas power systems. Today we shall start with axial flow compressors. In the previous lecture, we discussed the centrifugal compressor. In centrifugal compressor, the fluid was entering along the shaft. There was an axial entry of the fluid or air, and its exit was radial. It was entering the compressor. There was an impeller. Impeller was imparting energy or doing work on the incoming air, and then air was compressed, and finally we got high pressure gas or air at the exit of the compressor. Now, in axial flow compressor, the movement of the fluid is only in axial direction. That is why, because there is no change in direction, right? That is why the efficiency of axial compressor is more than the centrifugal compressor. In axial compressor also, like axial flow turbines, we have done their impulse turbine and impulse reaction turbine. Like them, in axial flow compressor also there are several rings or stages. Each stage consists of fixed blades and moving blades. So, arrangement is like this only, that there is a shaft. On the shaft, the blades are mounted, and there are moving blades, and there are fixed blades also, which are mounted in the casing. These are fixed blades. So, now in this case, the energy is consumed by the compressor. So, compressor moves with the help of a motor. The shaft rotates with a certain speed. Air is sucked in, and it gets compressed when it exits from the other end. So, air enters from here, right? It will go from first stage, second stage, third stage. It is shown converging because we have to maintain constant axial velocity. It is VA or VF. For designing the compressor, for the purpose of design of the compressor, this velocity has to remain constant, right? And in this direction, the pressure is increasing. When the pressure is increasing, velocity has to remain constant. We will have to reduce the cross section area or size of the compressor. That is why it is known, it is shown as converging passage, right? It has a number of stages. The stages may go up to 18, 20, 25, okay. And in this compressor, if we look at the stages, different stages, let us examine one stage of axial flow compressor. So, each stage has fixed blade and the moving blades, right? And suppose there is a fixed blade like this, and then there is a gap, small gap between these two, and then there is a moving blade. So, there are number of fixed blades, and there are number of moving blades, and they are mounted on the shaft. The shaft is parallel to this board, and it rotates with a certain rotational speed, and the air moves in this direction, axial flow direction. Now, in this compressor, like impulse turbine, if it works as an impulse turbine, then there is a no pressure rise in moving blades, there is only pressure rise in the fixed blades. So, it works as an impulse turbine, then there is no pressure rise in moving blades, there is pressure rise only in fixed blades, that is in fixed. These are fixed blades, they are moving blades, right. Regarding velocity, velocity will definitely increase in moving blades, because the kinetic energy will be imparted to the moving air, and this acts as a diffuser, so velocity gets reduced. Okay. but normally the axial flow compressors, they work as impulse reaction turbine, reverse of inverse reaction turbine, not impulse reaction turbine, reverse of that. So, here the pressure, there is a pressure rise. If we see the pressure rise, so there is a pressure rise in moving blades and fixed blades as well, right. And regarding the velocity increases in moving blades and it falls in fixed blade. Now first of all, we will do what we will do, we will draw a velocity diagram for the axial flow turbine, that will make things clearer. So, there is a blade in a axial compressor, not turbines, axial flow compressor, velocity diagram for an axial flow compressor. The air is supposed to glide over the surface, right. When the blade is moving in this direction, the air is supposed to glide over this surface. So, this is VR1, right, and the blade is moving with a certain velocity in this direction. So, it is U. Here we do not have U1 and U2 in centrifugal compressor, because there was a radial flow. So, we had U1 and U2, two different peripheral velocity at the impeller, inner diameter of the impeller and outer diameter of the impeller. Because here the flow is taking place in axial direction, so there is only one peripheral velocity, that is U, and this is the absolute velocity of air through which it will be entering the blade. So, in axial flow turbines, the angles are, the axis is taken, the shaft axis is taken as a reference. In earlier, in the reaction turbine or impulse reaction turbine, the peripheral direction of the peripheral velocity was taken as a plane of reference, right. Here axial direction is taken as a plane of reference. So, axial direction when we take as a plane of reference, then this becomes V1, right, and this is VR1, right, and velocity U is this, and this is the velocity U. Velocity U is perpendicular to the axis of the shaft, okay. And now this is V1, VR1, sorry, this is V1, this is VR1, this is U, so this is angle alpha 1, this is angle beta 1. Regarding exit also, the triangles are like this, because then this is VR2, right. So, regarding axis also, this is V2 and this is VR2, this is alpha 2 and this is beta 2 and this is U, and this is V1, V2. Now, here in axial flow compressor, there is one more thing to discuss. The work in a stage is equal to, in axial flow compressors, the work in a stage is equal to VR1 square minus VR2 square divided by 2 plus V2 square minus V1 square by 2. Here peripheral velocity component is missing, because there is nothing like U1 and U2 here, there is only one constant peripheral velocity. So, energy imparted to the fluid by virtue of change in peripheral velocity is 0, right. So, if you look at this, then per stage work in axial flow system, we can say, is less than the per stage work in centrifugal compressors, right. Now, here this is axial velocity VA, or it is velocity of flow also, VA, velocity of flow, right. So, u is equal to, if we take these two triangles, then u is equal to V A tan beta 1 plus V A tan beta 2, or we can say u by V A is equal to tan beta 1 plus tan beta 2. Similarly, for this triangle, u is equal, sorry, not beta 1, sorry, it's wrong, beta 1 and alpha 1. This is alpha 1, not beta 2, alpha 1, tan alpha 1. Now, in this triangle, VA tan beta 1, beta 2 plus VA tan alpha 2. So, again we can take u by VA is equal to tan alpha 2 plus tan beta 2, or we can say that these two, if you compare these two, then tan alpha 1 plus tan beta 1 is equal to tan alpha 2 plus tan beta 2. So, this relation is frequently used in the analysis of axial flow compressors. Now, we will calculate the tangential force required to compress the gas. Tangential force is VW2 minus VW1 for the mass flow rate of 1 kg per second, otherwise it will be multiplied by the mass flow rate also. And then work is F into U is equal to U VW2 minus VW1. And VW2 is this. VW2 is will component at exit, this one, VW2. So, VW2 is equal to VA, so U is there, VA tan alpha 2, VA is axial velocity minus VA tan alpha 1, right, and then we can say it is UVA tan alpha 2 minus tan alpha 1. If you use this relation, then work is UVA alpha 1 minus tan alpha 2 minus tan alpha 1, tan beta 1 minus tan beta 2. So, either of these expressions can be used for finding out work done on the gas or air during compression in an axial flow compressor. Now, temperature change in a stage, because in compressors normally we have to find the temperatures at different stages. So, temperature change in a stage, del T is equal to, we will take the work tan beta 1 minus, let us say, tan beta 2, right, and delta T stage per stage is Cp delta T. So, divided by Cp, that will give the change in temperature in a stage. There is a expression we will discuss it later on, that is work done factor. It will be multiplied by the, when we want to have actual temperature rise, it will be multiplied by the work done factor. And if you want to have pressure ratio in the stage, that is going to be 1 plus efficiency of the stage delta T stage divided by del TO1 gamma over gamma minus 1. TO1 we have taken stagnation temperature at inlet, because we have considered the kinetic energy also. So, when we consider the kinetic energy is converted into the pressure energy, which will result in the rise in temperature. So, this is the expression for pressure ratio in a stage. Now, we will do the pressure rise. So, what we have calculated done so far, we have just discussed the working principle, we have discussed the velocity diagram, we have discussed the work output. Now, pressure rise and aerodynamic force in a stage of an axial flow compressor. So, we will start with Buttonless theorem, P1 by rho is equal to V1 square by 2 is equal to P2 stage divided by rho plus V2 square by 2, because it is moving in horizontal direction. So, potential energy is 0. So, delta P is half rho V1 square minus V2 square. Delta P, this minus this, is equal to half rho V1 square minus V2 square is equal to half rho. Now, if you draw again this diagram, this is V1, VR1, U, beta 1, alpha 1. So, this is VW and this is VA. So, it is V1 is VA square plus VW square. In same fashion, if we take into account this diagram, alpha 2, beta 2, VR2, V2 and U. Here also the V2 square is VA square minus VW2 square. Okay. And then this will be cancelled out, it is going to be half rho VW1 square minus VW2 square, or it is half rho VA square, and the VW is nothing but VA10 alpha 1. So, 10 square alpha 1 minus 10 square alpha 2. So, only axial velocity is with us and the density with us, we can find the pressure rise in this stage. So, axial force. Now, once we have the pressure rise, pressure multiplied by area will give the force. So, axial force is, this is S, LB is the length of the blade, rho VA square 10 alpha 1 minus 10 alpha 2, 10 alpha 1 plus 10 alpha 2 divided by 2, or this is mean blade angle, alpha 1 10 alpha 1 plus 10 alpha 2. So, it is, or we can replace this by 10 alpha m. It is not the angle of mean of the angle, but mean of the tens of the angles, right. So, this is axial force. Now, the compressor will also experience the whirling force, which is perpendicular to this one. This is a compressor. So, a compressor will have, the force will be exerted in axial direction, force will also be exerted in whirling direction, and that force is mass flow rate multiplied by VW1 minus VW2, and that is VF SLN rho. This is volume, this is density, VW1 minus VW2, and the net energy consumed by the axial flow compressor will be Pythagorean sum of this. It means net force is going to be equal to under root this force, square of this plus square of this, and the direction of the force will be the ratio of these two, and that is going to be this Fx divided by Fwsi, Fx divided by Fwis, and that is going to be equal to tan alpha m, because these terms will be cancelled out. This is Va. So, these terms will be cancelled out and we will be getting the ratio of these two as tan alpha m. Now, before dividing it, we can write Vf or Va square as as length of the blade rho. Vw1 is the V1, that is why square has come here. This is cos alpha 1 minus, sorry, not cos, tan alpha 1 minus tan alpha 2. Now, they will be cancelled. Now, if we take the ratio of this and this in order to find the direction, then we will get all these terms will be this term and this, they will be cancelled out, and this will also be cancelled out, and what we are going to get is tan alpha m, right. So, we have calculated force required in axial direction to compress the gas, force required in the peripheral direction. This is the force in axial direction, this is the force in peripheral direction, and then Pythagorean sum of these two forces will give the net force required for compressing the gas, and their ratio will give the direction, right. Now, we will solve one worked example for axial flow compressors. Calculate the pressure rise and work done by a rotating cascade of axial flow compressor for the following data: peripheral velocity 200 meters per second, flow velocity is, or Va, axial velocity is 186 meter per second, and alpha 1 and alpha 2 are given. Rho is equal to 1, that is density of air or working fluid. Assume isentropic compression. So, delta P pressure rise is half rho Vf square tan square alpha 1 minus tan square alpha 2. We have already done that, right. Now, here delta P is equal to half, rho is given here 1, velocity of flow is 186 square, tan square alpha 1 is 45 minus tan square alpha 2 is 14, and this gives the pressure rise as 16.22 kilopascal. That is the pressure rise. Calculate the pressure rise and work done by rotating. So, work done is U Vf tan alpha 1 minus tan alpha 2. Simply we will put the values. U is 200 meters per second, 200 minus Vf 186, tan 45, sorry 45 minus tan 14, and this will give the work done as 25.9 kilowatt. This is the work or energy consumed by compressor for the movement of air or for the compression of air. And after this, we will take another numerical which is a little lengthier. In 8-stage axial flow compressor, so there is a axial flow compressor consisting of 8 stages. The overall pressure ratio is 5:1. So, compressor has number of stages, right, and cumulative effect of pressure rise is 5:1, and the overall efficiency of the compressor is 90%. The temperature and pressure at inlet we will write down here, so that later on time is saved. So, the temperature and pressure at the inlet, so T1 is equal to 20 degree centigrade or 293 Kelvin. We will just add 273 here, 273 plus 20 is equal to 293 Kelvin, and that is T1. And 100 kilopascal pressure, P1 is equal to 100 kilopascal. The work is divided equally between the stages. So, on each stage same amount of work is being done on the gas. The mean blade velocity is 175 meters per second, and 50% reaction design is used. When there is a reaction is 50%, then alpha 1 is equal to beta 2 and alpha 2 is equal to beta 1. As we did in the case of turbine, same thing will be done here. Here also in axial flow compressor, if the degree of reaction is 50%, then this nozzle inlet angle is equal to blade outlet angle, and nozzle outlet angle is equal to blade inlet angle. The axial velocity throughout the compressor is constant or equal to, or Vf is equal to Va is equal to 100 meters per second. Okay. So, we assume there are 8, how many stages are there? There are 8 stages. So, Z is denoted by the stages. So, Z is equal to 8, right. There is a pressure rise in each stage, and the temperature at the outlet of the compressor TOZ by TO1. TOZ means after the 8th stage, that is POZ by PO1 raised to power gamma minus 1 over gamma. Okay. If the compression index is not given, we will assume it to be gamma. This is so TOZ is equal to TO1 POZ by PO1 raised to power gamma minus over gamma. Because index of compression is not given, we have assumed it to be gamma, is equal to TO1 is 293, POZ by PO1 is 5, 0.286. This gamma is equal to 1.4 minus 1 divided by 1.4 is equal to 0.286. So, directly we have put the values, and then TOZ we are getting 464 Kelvin. So, TOZ 464 Kelvin, and the compression is not isentropic because the efficiency is given. Efficiency is 90%. Overall efficiency is 90%. So, is equal to TOZ minus T1 divided by TOZ dash minus T1. TOZ dash is equal to T1 plus TOZ minus T1 divided by, now T1 is 293 plus TOZ we have taken as 464 minus 293 divided by 0.9, and that gives TOZ as 483 Kelvin. So, TOZ dash is 483 Kelvin. Same thing we have done as we did earlier also. Now, work is, if we take as a thermodynamic process, then work is equal to Cp TO Z dash minus TO1. This is the work done on the gas, and this is equal to CW2 minus CW1, sorry, VW2 minus VW1 multiplied by U. This is work in one stage multiplied by number of stages, right. This is the work, this is not the work in the entire compressor, because this whirl component is only for one stage. So, this work multiplied by the peripheral velocity multiplied by the number of stages, this will give Vf tan alpha 2 minus tan alpha 1 uz. Okay. Now here we can get the value of tan alpha 2 minus tan alpha 1, because this is equal to W. Now here we have the value of TOZ dash 483 Kelvin, TO1 293 Kelvin, and U is also given 175 meter per second. So this is 175 and this one is 8, this is 175 and this one is 464 and TO1 is 293, right, and this is equal to this one, both are equal. From here we will get the value of tan alpha 2 minus tan alpha 1, and tan alpha 2 minus tan alpha 1 is 1.3639. Okay, that is equation 1. And second one is, we know that U is equal to Vf tan alpha 1 plus tan beta 1. If you look at the velocity triangle, alpha 1 and this is beta 1 and this is V1, VR1 and this is U. So U is equal to, this is Vf. So U is equal to Vf tan alpha 1 plus tan alpha 2, or U is equal to 175 and Vf is 100 is equal to tan alpha 1 plus tan beta 1. Okay, and this is equal to tan alpha 1 plus tan beta 1 is equal to 1.75, 175 by 100. Now add these two, you will get tan alpha 2 minus plus tan beta 1. So if you add these two, this will be cancelled out. If you add these two, then this will be cancelled out. Then tan beta 1 plus tan alpha 2, and beta 2 is equal to, beta 1 is equal to alpha 2. So we can comfortably say that tan beta 1 is equal to 1.3639 plus 1.75 divided by 2. And from here we will get the value of beta 1, and the beta 1 is 57.4 degree. So beta 1 is 57.4 degree. So once we have the value of beta 1, we can either of the equation, from either of the equations we can calculate the value of which angle is required, the next calculate power required, and blade angles. So beta 1 is with us, we can calculate the value of alpha 1, and once alpha 1 beta 1 are with us, we can find the value of alpha 2 and beta 2. So here the alpha 1 is 10.95 degree, it is equal to beta 2 and this is equal to alpha 2. So all blade angles are known here. That is all for today, and in the next class we will start with the characteristics of axial flow compressors.